Great. So very warm welcome to everyone. It's a lovely afternoon here in Lausanne. And we have the great pleasure to host Professor David Ceperley for our CECAM and MARVEL series of classics in molecular materials modeling. This is something that we coordinate together with CECAM, Andrea Cavalli and Sara Bonella. And we are actually hosted in their headquarters here, and MARVEL, that is a Swiss Center on Computational Design and Discovery of Materials. On one hand, I mean, David doesn't need any introduction. On the other hand, it's very pleasant to always do one. Is really, you know, one of the founding figures of quantum Monte Carlo methods. This is in particular what we are going to discuss today. David got his bachelor degree from University of Michigan, and then he got his PhD from Cornell. Thank you. I should have prepared better. But following the PhD at Cornell, he actually came to Europe, to the University of Paris. So that would be maybe a topic for later discussion. He did a postdoc at Rutgers University, so that's a trait that we share. And then he joined Lawrence Berkeley and Lawrence Livermore National Laboratory as a staff member before moving in 1987 to the University of Illinois Urbana-Champaign as a faculty member, where also one of the very large supercomputer center is located, apart from being in the Department of Physics. David is a fellow of the American Physical Society. Is a member of the, of course, National Academy of Science, and is a member of the American Academy of Arts and Science. So without further ado, let me actually, before we start, mention, you know, well, what the CECAM and MARVEL classics are, where we invite the originator of milestone conceptual steps method and algorithm. And one of the nice parts of this event is that we don't have only a lecture, but we also have an interview with the speakers to try to give a slightly more human side of what it is to be a researcher in the field. And since we have a captive audience here, let me also mention some of the other events that will take place. Actually, on Thursday, we will have Gerd Seder give one of the MARVEL distinguished lectures. And on February 28th, we will have here an event, what we call actually a Marianne Mansay conversation, following sort of the first one, where Marianne Mansay that actually coded many of the molecular dynamic codes that Bernie Albrecht used. So she gave the first one. We'll have one on science and diplomacy. So with this, let's give the floor to David, and we'll switch to the computer here.
How do we do that?
It's almost automated. I guess I could have done it. Sorry.
It's okay.
Okay, well, thank you for the introduction. It's nice to be back in EPFL, although unfortunately the rain kind of reminds me of being in Lausanne this time of year. I was here in 1994 with Roberto Carr and Julie Galli and Francois Gigi were here at the another center that in another building here, but that was before CECAM was here. I have been back many times to CECAM, and in fact, I'm coming this week to CECAM. Okay. What I'm going to talk about is actually kind of a mix between a history and a little bit about Monte Carlo, although you won't learn very much about it. I'm sorry, I'm not teaching about Monte Carlo today. But then I'm going to come to a little bit about what we're doing with machine learning, maybe give you some future directions, what we're doing and what I think is a big future of quantum Monte Carlo. So let me get started. Okay, where Monte Carlo starts is in this paper by Metropolis in 1953. It's a long time ago, but you know, that's really, they introduced one of the top algorithms in computational physics, Metropolis method. You know, I'm sure everyone here is familiar with it, with the idea of a Markov chain. And it was about 10 years after that that the first quantum Monte Carlo calculation, the first serious one, took place by Bill McMillan, a graduate student at the University of Illinois, who did this. He was lucky that Bardeen was his advisor and let him go and work on this problem. And he did what we call variational Monte Carlo, VMC, 60 years ago. He used Metropolis technique that I showed you had been developed 10 years before. And he realized that you could map a classical system onto a quantum system using the Jastrow wave function. And so you could use a code. These were codes not in Python or Fortran, but in assembly language back then, with cards and with wires and things. And he did some very important physics back then. He verified that this kind of a wave function describes superfluid helium. That is in terms of getting a pretty low energy and calculating the condensate fraction, how much, the fact that it's a Bose condensed system back in 1964. And there were a lot of new methods that we use today. How do you optimize wave functions? How do you calculate energies and expectation values? If you think about the kind of computer that he did it on, you would be amazed. I mean, basically, it was called an Iliad computer. It was the first computer that had transistors. It had 8,000 words of memory, the total memory, and but he did up to 108 particles in this. So you have to manage your memory very well. And you had fast memory and slow memory. And the slow memory was actually a drum that revolved and mechanically, right? And it'd be like reading off of a magnetic tape. This is going around in circles, right? So the fast buffer was 25 microseconds. So anyway, what is variational Monte Carlo? In case you don't know this, you're not going to get very much about methodology, but basically the variational principle you all know about. You take a wave function and you have a Hamiltonian, H. I guess I'm supposed to use this mouse here. And this is the Hamiltonian here, whatever it is. In this case, it was a Lennard-Jones potential.
Sorry, David, are you changing slides?
Oh, I did change slides.
Aha.
Yeah, it didn't change here, did it?
Mysterious, this has never happened before.
Okay.
It's the first one.
25 microseconds.
That's right.
Let's try again.
Shall we try again?
Uh-huh.
So none of my slides changed.
And may I just put the laser pointer so it's more visible, even though it's quite small.
Okay, I'm sorry, these weren't up there before. Wasn't looking back there. Okay, so anyway, these are the papers in physical review of Macmillan. And here's the picture of Macmillan. Unfortunately, I never got to meet him. He died in a bicycle accident just before I moved to Illinois. So anyway, he's a pretty well-known physicist because he did a lot of work on superconductivity after the variational Monte Carlo. So anyway, this is what I was explaining about variational Monte Carlo. That basically you have a Hamiltonian and a wave function, and this gives you an upper bound to the ground state energy. And the basic idea is you sample your coordinates from the square of the wave function using the Metropolis technique. And then you take the average value of the local energy, which is this quantity here. And then you just multiply and divide by the wave function to prove that. It's not very complicated. And then the variational part is considering if you have any free parameters in your wave function, you try to vary them to get the best possible upper bound, right? That's the variational part. Now, the recent wrinkle, where Giuseppe is an expert here, is to use a neural network to make a general class trial wave functions. And you can do much better, of course, than we did with the Jastrow wave function by making an expanded functional class. The problem is, as you will learn in this field, is that it's actually very slow to optimize and compute those, a completely general function. But somebody will figure out how to do it, I guess, and it will be the future. But right now we work with pretty simple wave functions, or at least Macmillan did. So it's still working. Okay, so that was in variational Monte Carlo was in the 1960s for bosons, that is not considering anti-symmetry. The real revolution came with one of my advisors, Mal Kalas, shown here, who wrote this paper in 1974 with Dominique Levesque and Lou Verlet, which I call KLV, is doing an exact calculation of hard spheres with what's called projectile Monte Carlo now. Okay, and so that was 50 years ago. And this was really a revolution in terms of being able to do an exact solution of 256 hard spheres. You remember that Bernie Alder did molecular dynamics of like 256 classical spheres, and this was the equivalent for quantum mechanics. So this was a model for liquid helium-4, again, as hard spheres. It's basically a very good model for liquid helium-4 hard spheres, because it's mostly the repulsive potential that's important. But in this KLV paper in 1974, he put together a lot of the QMC techniques that are still being used in projector or diffusion Monte Carlo, including a drifting, branching, and diffusing random walk. It was different in that it had no time step error. They didn't talk about imaginary time, but it was in there. Believe me, it was buried deep inside the code. It wasn't obvious when you read the paper. And they used importance sampling, which is essential if you're going to do very many particles, like more than 5 or 10 particles, to do importance sampling. And you have things like ensembles of populations that you evolve in imaginary time, and you have population control and so forth. So that was all in this paper, and that was when I was a graduate student. And so this is what I started working on. And here is a little bit of mathematics. What is projector Monte Carlo? Well, it's basically just this simple statement that if you take a trial wave function here, phi of 0, 0 means the imaginary time, and you use the Hamiltonian to project out the excited states, you'll end up with a ground state at large t. And so this is what's called projector Monte Carlo. And it's so at large state. So this, how can you do that? That's because this operation turns out to be a diffusion and branching operation. And so, but the trouble is that this wave function can only be described as a probability for a bosonic system. And so this is where the fermion sign problem comes in. If this is a complex wave function, it's not a probability. So even though this operator is a probabilistic thing, what you're starting with is not a probability. So that's the fermion sign problem, which I'll talk about in a few minutes. So for the ground state of a non-relativistic Hamiltonian, you can solve. That's the bosonic problem. Or one-dimensional problems you can solve. But generally, in quantum mechanics, you can't, and that's the sign problem. Now, so going back to my historical development, this is when I was a graduate student. This was one of my first papers. One thing you notice is this is what happens when you write a thesis and you let your advisor submit the paper. He doesn't proofread it. So I had a typo in the title of the paper. It was not a Monte Carlo simulation of the study. It was a system, right? But anyway, you can see that these were back in the days when a secretary had to type your paper and then they sent it in the mail to the journal and then they sent back the proofs, but I was already in Europe, so I couldn't see the proofs. So I never had a chance to see the paper until a year later. But anyway, this is where we did the first mini fermion calculation, and it was again variational Monte Carlo. And we had some of the new features we had to deal with is how to treat the anti-symmetry. And I'll discuss that in a minute, but well, I think I'll get to these points later. These are my advisors, Jeffrey Custer and Mount Kalos. So what was new? Why was there a 12 years between when Macmillan did bosons and then we did fermions? We did helium-3, for example, instead of helium-4. Well, it's because, first of all, anti-symmetry was required. This is one of the things that I've learned is there's often a psychological barrier to people. People said, well, that determinant, that's going to be really bad to do. You don't want to do determinants. And so they would find all kinds of ways not to do determinants. But eventually we said, well, let's just do the determinant. It's straightforward. And so why didn't we want to do the determinant? First of all, we thought determinants have nodes. They're places where the wave function vanishes. It divides space between positive and negative. We thought, oh, you'll get trapped. You won't be able to see, you won't be ergodic in all of phase space. But that wasn't true because we found the random walks can easily jump over these zeros. First of all. Second, a few years later, we proved that they don't have to jump over because the other side is exactly like the side you're on. So you don't need to by symmetry. But I should say we use real orbitals to avoid complex arithmetic. That's the other reason people didn't want to do it, is they thought, well, it'd just be so slow that you won't be able to do anything. But actually we found out linear algebra is something that computers do really fast. And we found a quick way to do the determinants are normally in cube, but we learned something that statisticians knew about is a way to do updates of these determinants or only in squared instead of in cubed. And so that made things faster. And so we could actually do a few hundred fermions without too much trouble. So here's the kind of a computer equipment we have. It was called a CDC 7600, but nowadays all the students I see are sitting there looking at their monitors or looking at their phones or whatever. This is what we looked at, our card punches. We had to type out cards one at a time, no typos allowed. And then you make a deck like this. You couldn't drop the cards. You had to keep them clean and in order. And you had to read them in the machine like this. And then you had to wait 24 hours to find out if you had any bugs or not. So that was our graduate student life, actually doing that. And then 10 years later, we could put things on tapes like this, big tapes, and we could read them in. But every computer vendor had a special way of reading and writing the tapes. And you could not go from IBM to CDC successfully. Anyway, I then, after I did the variational calculation, I went to Paris and I worked in the group of Relay. And there we had the same thing, punch cards, a different kind of computer. But as my project as a postdoc, I decided to work on electron gas. And that was kind of it was because people were talking about two-dimensional electron gas on the surface of helium. And now 40 years later, this subject is back with these Moiré lattices and graphene layers and so forth. But so they never really realized it back in the 70s, but now you can do experiments on it. But I developed these techniques, Ewald sums. That is, I didn't develop Ewald sums. I put them in the variable Monte Carlo. One of my big breakthroughs was to make a trail function that had no parameters. So you just had to put in the electron density, the dimensions of space, the number of particles, and then it would no optimization of the wave function was necessary. And it had all the right physical conditions cusp condition, long range potential. And then I was very rapidly able to look at physics, like when does a Wigner crystal form? When does it become ferromagnetic and so forth? What is the energy of the electron gas and so forth? And so that was what I worked on these ancient machines that had punch cards and so forth in Paris. And then I moved to Berkeley, and I then took this code, variational code, and changed it into projector Monte Carlo code. And I did the same thing, and this is where quantum Monte Carlo intersects with density functional theory, because this was the calculation where it was used back in the 80s as the basis for the exchange correlation function, the diffusion Monte Carlo calculation of the electron gas with Bernie Alder. And basically, it was basically the code that I wrote as a postdoc in Paris, and then generalized to do projector Monte Carlo. So I got a lower energy because I'll explain in a second. But again, there was no longer punch cards at that point. We could enter things on a computer monitor now. But we had only about 2,000 lines of Fortran code. We had a vectorized machine, which is kind of like a GPU, but we only had about 50,000 words of core memory. And what is the diffusion Monte Carlo algorithm? Well, basically, I took what Kalos had done with his exact projector Monte Carlo method, and I simplified it in something called diffusion Monte Carlo if you write out, this is the master equation for projector Monte Carlo. If you apply an importance sampling where you multiply by the trial wave function and you write the master equation for this F function, you get this master equation, which, because I had worked for a year with polymers, I could recognize it as a diffusion, drift, and branching process. And so then I came up with this idea of diffusion Monte Carlo. That is, you have a diffusion term here, you have a drift term here, and you have a branching term here. So basically, I recognized what was in Kalos's projector Monte Carlo as this form. It was simplified so I could do much more complicated problems, whereas he was sort of limited to these hard spheres. The screen just went blank. Oh, okay, good. And the other thing that we introduced, because I worked for that year with polymers, is to put in rejections. It's called a hybrid method, where you do an evolution and then you accept or reject. So that way it has much smaller time step errors than if you don't do the rejection. I used months of cray time, which sounds like a lot. And I think the rest of the world was kind of envious. One particular occasion, California is subject to earthquakes from time to time. There was an earthquake that hit when I was doing production on the electron gas. And my assistant, Marianne Mansai, that you heard about, we're going to have the Mansai lecture in a few weeks, who I work with every day in this period, because I didn't have a security clearance, so I couldn't use the computers. She had to be my hands-on. So I would tell her, change the density to 20, change the time step to 3. On the phone, I would tell her that, and she would run it. The earthquake hit, she put my program on every cray at Livermore, about 4 or 5, and it sat there for 2 weeks without any interruption, running for the whole time. So a few densities, I have really small error bars because it ran for weeks at a time on the world's fastest computer at that time. We'll come up to that in a minute. She would then physically print out the output and mail it to me. This is regular snail mail to me in Berkeley. And then I would look at it and say, well, I messed up that run. I should have done something else, but oh well, 2 or 3 days. So this is how we worked. And so you see, it was really good that I developed these techniques to make things automatic, because I would never have been able to be fiddling around with the code. I had to plan out the things and run it a week time scale at a time. And I couldn't be changing it like every 15 minutes. So, anyway, so what is this? The main limitation was what we call the fixed node. That's the way we solved the sign problem. And so basically, the idea is this is your unknown wave function, the exact wave function. This is your trial wave function. The fixed node means if you're dealing with real wave functions, you want the product of this to be positive of these two. So when this trial wave function vanishes, you want your exact wave function vanish. So what you're effectively doing is dividing the unknown wave function into a modulus and a phase. You're keeping the phase or the nodes fixed, but the modulus could be anything, but it has to be positive. And you get the best possible, or it goes again. Okay. You get the best possible upper bound. See, this is the variational energy. This is the exact energy here, E0. So the fixed node is the best possible upper bound with that constraint, right? So typically you recover about 90% of the correlation energy that's missing in your variational wave function. And if you happen to get the right wave function, the right nodes, then you get the exact energy. And it scales just like variational Monte Carlo, like n cubed or better. And you can generalize this thing. I presented it as a real wave function, but you can also talk about complex wave functions or lattice models or finite temperatures. And there's a generalization for those conditions too. This sign problem, that is to go beyond this approximation, well, I'm not going to talk about it, but it was interesting. A few years later, I discovered this quote in Feynman and Hibbs' book on path integrals in 1965, and he recognized the sign problem in the path integral language. That is, he developed his theory of imaginary time path integrals that describe superfluidity. And he says, well, it would be nice to do this for fermions too, but he hasn't figured out a way of doing it. In a way, we figured it out with our restricted paths, but it's somewhat approximate. So anyway, it was interesting that Feynman had discovered this back in the 50s. Now, we held our first quantum Monte Carlo meeting in Paris, 1982, which I attended. And these are some of the things that we were working on back then. Helium droplets as a model for nuclei, mini fermion systems, chemistry, quantum spin models, lattice gauge theories, things that are still going on today. The applications of diffusion Monte Carlo followed in the 1980s. Generalization to molecules. There's a whole branch of people that do chemistry, not particularly me, although I did write with my postdoc, Peter Reynolds, one of the first papers on applying this method to molecular physics. But we started doing dense hydrogen back then, which we're still doing. And we did other problems like muon physics and so forth. But the other branch, the thing that we actually worked on a lot in the 80s was to do things at finite temperatures. How do you connect the ground state quantum systems to classical simulations where you don't have quantum mechanics? And that's what path integral does. And it started with this paper of 1953 of Richard Feynman on how we describe a superfluid helium, how you understand that in terms of imaginary time path. So essentially what Roy Pollack and I did in 1984 was to just simply take this imaginary time path integral and apply Monte Carlo to it. But there were a lot of tricks that we had to invent along the way. And here's the kind of the picture of path integral solution of bosons. This is a 6 bosons in this box, in two-dimensional box, at high temperature. You have these black points, black circles, which are the boson. Each one turns into a path, which is like an elastic band, right? And so what Feynman did is he said that you can do the quantum mechanics of these 6 particles in terms of all the ways of moving around these particles and stretching the band. As you go down to low temperature, the band gets longer and longer, right? Except when you have bosons, something else happens. They're allowed to reconnect. And so this is what happens when this rubber band, the elastic band, gets bigger and bigger. They're allowed to reconnect with their neighbors, and you get this kind of picture here, where you have a path like this, and this is called a winding path because these are periodic matter conditions. And this is actually what's involved in Bose condensation within Pythagorean Monte Carlo. So you have to do the sampling both of the paths and the connection of the paths behind Monte Carlo. And we sort of generalize this to fermions a few years later. Okay, maybe I'll skip over this. I just wanted to show you this one slide though about the computers. I looked up this graph of how much computers have changed since I did all of that work you're talking about. Here is today's computer here. 1 second on a powerful computer, probably in Switzerland or in the United States, equals all of the time that I used in the 1980s, basically. If you look at the scaling of 10 to the 9th in computer power. So even though I had access to like running these giant Cray computers for weeks at a time, that corresponds to fractions of a second on today's computer in terms of how many flops you could conceivably get out of them. That's assuming. Of course, we worked really hard on optimizing our codes, and I'm not sure that that happens anymore. Here is the work environment. I've said a little bit of this before, but LaTeX, that was a big change when it was introduced in the mid-80s. The internet started being useful in the 1980s, and I came to Italy as a sabbatical in 1986. Here we go again. But what a revolution. Instead of sending those terrible tapes, which would never work, I could send my files on the internet. And this was what I had to do. You had things called BitNet and ARPANET, and you had to send things from one network to another network on servers. This was the instructions that I gave to somebody to send me things. Here's the first chance that we had to work at home. We had something called a Silent 700, which like a typewriter, and you put your phone in here. Of course, when you were using the phone, no one else in your family could call in or out. It was only 300 baud. And then it would write on this terrible tape.
Let me give you power, maybe it helps keeping it awake.
Oh, you think that's the problem?
Oh,
Except I don't have another port.
No, it is, but it is connected. No, it is connected.
Yeah, okay. Anyway, but I remember when my daughter was a baby, then at the middle of the night, I could check on my jobs and see if they were running and print out the results. Anyway, let's skip over this. I wrote this in 1995 when we were required to put up a website, and I put down top reasons why nobody uses quantum Monte Carlo. The number one reason is there were no codes that people could use except in our own research group. So that's why nobody else would use it. It's still somewhat true. And some of the other reasons were, well, we really like to do dynamics and other things. So anyway, there have been a lot of development since then. One of the development is pseudopotentials, trial wave functions. There are a lot of much better trial functions. There's a lot of codes available now. There's a lot of ways to correct, get rid of some of the systematic errors. There's other methods like auxiliary field, quantum Monte Carlo, rotation, and so forth. So we've discovered a lot of things. I won't talk about that actually. We plan to have another speaker today to talk about some of those things. But in the last, since the 90s, we discovered many interesting things, and it's made some big impact, for example, in Bose condensation and some other areas. But the continuum quantum Monte Carlo is focused on energetics of ground state structures, like what is the energy of this state versus that state, where you do heroic calculations to get small error bars. But the computer time requirements are extreme, and the optimization for the wave functions is extreme. I think a lot of the applications is probably you do in MARVEL and certainly in the CECAM workshops are to look at disordered systems, phase transitions, mesoscopic systems, that is systems with thousands or millions of particles. We want quantum Monte Carlo to have an impact in those fields. And something that, you know, I guess back about 5 years ago, I was convinced that machine learning actually worked pretty well. I mean, I read some of the papers, and so we decided to try it. I mean, it's a great opportunity if you can get first principles accuracy at a much reduced cost. If you can make bespoke potentials, that is potentials that are tailored, this is interatomic potentials tailored to a specific situation, to a specific group of elements. However, you know that if you're going to do machine learning, you have to train your model, and you need a lot of accurate data to train your model. How are you going to do that? And I think that's where quantum Monte Carlo can really step in. That is, there's an opportunity where we could enable that, and I want to try to convince you of that. Why do I think that? Well, it has a lower bias than DFT, generally has a higher accuracy. It's not perfect, but it's because you have these upper bound properties, you kind of know when you're getting better. Okay, so, you know, generally you have you don't require an experiment to tell you if you're getting better. Particularly continuum quantum Monte Carlo is good because these disordered systems are moving around, and if you have a lattice, you have a problem with the lattice biasing the results. And also, of course, quantum Monte Carlo is naturally parallel because you can generate, we want to generate a lot of data, and each processor or node of your computer can be working on a different configuration to generate more data. But what about the noise in quantum Monte Carlo? Here's a very simple example. If you have a quartic potential, and then you want to train a potential to fit this data. And suppose the quantum Monte Carlo generates this data with the error bars, which has an error of 1 by definition in this model. Then you do a fit to this data. How accurate is the result of your fit? Well, it's 3 times better than the data. Why? Because you have 50 data points here, and you represent it by a polynomial which has only 4 terms. So naturally, you basically average out a lot of the noise. And this is a general property. That is, if you give your model a lot of noisy data, if your model is reasonably smooth, your noise will be much reduced over the quantum Monte Carlo. And basically, this is a general property of quantum Monte Carlo, that extra averaging is almost free in Monte Carlo. If what we're doing when we're fitting a model is minimizing something like chi-squared. P of R is some distribution of coordinates that you have, like the Boltzmann distribution or something. And here is the quantum Monte Carlo data, and here's your model right here. You want to minimize the mean square displacement. In explicit methods, such as density functional theory, if you do 10 times as many configurations, it'll take 10 times as long, right? But with quantum Monte Carlo, it won't take 10 times as long. It will, because you can run them each for 1/10 the time. And the noise will grow up, but you'll get more points in your database. And so the noise will grow up by a factor of square root of 10, but you won't increase the computer time. So the advantage is you can cover phase space. So like here, this is our phase space. So if you try to represent this by just a couple of points, and the exact method would be better. But if you don't know where you want to put your points, it's better to like spread them out kind of uniformly. So this is especially important for a complex system, because there's so many ways that the atoms can arrange themselves. So here's kind of there's a geometry to these errors. So here's the exact potential right here. And this is the noisy data. And there's some error. The noisy data, because quantum Monte Carlo has noise, it's Monte Carlo. And this is the model. You see the model is generally much closer to the exact result. And the interesting thing is you can figure out how close your model is to the exact result. Even if this epsilon, this error, is much less than the noise in your Monte Carlo sigma, you can basically it's because the noise in epsilon is uncorrelated with the noise in the quantum Monte Carlo. And so they have to be orthogonal to each other. And you can basically use this rule. You can essentially subtract out the errors of the quantum Monte Carlo and figure out how good your model is. And I should have showed you my picture here. So here's an example that I'm going to talk about with hydrogen. So I still have, what, 15 minutes. So I'm going to talk about mini-body hydrogen now. And this is an example of this geometry of the errors. So we have a distribution, a database of hydrogen where we sampled a lot of configurations. We sampled 20,000 configurations. Then we computed quantum Monte Carlo forces and energies. And then we fit it to two different models, a deep MD model and a MACE model. And this shows you how close, this is the exact result for the Born-Oppenheimer surface, the red dot. And this shows you how close the MACE model is. This is 2 EVs here. This is for 96 atoms, it's not the energy per atom. It's in the total system, 2 EVs. Here's the deep MD model. But look at DFT. This is how far off DFT is from the exact answer. You see these distances are much greater than here. It's all on scale. The errors are like 3 or 4 times bigger for DFT. And it also shows if you're going to model mini-body molecular hydrogen, you're much better using van der Waals. Big surprise, right? Van der Waals has dispersion interactions than you are using PDE, density functional. But the machine learning model is way better than DFT, right? This triangle is much smaller. This is for the energy, which controls the thermodynamics. These are the forces over here that control the dynamics, the classical dynamics. And it's not so good on the forces, but again, this is controlling the thermodynamics, the energy. The forces are controlling the dynamics. But still, the model is much better than DFT. That is better than DFT, maybe a factor of 2. I forgot what I was going to say. So let me back up and talk about hydrogen a little bit. Why do we study hydrogen? Well, I say that sort of 3 reasons. First of all, there's lots of important applications. Hydrogen is ubiquitous, both in astrophysics and in fusion, but it's also a common element, right? In chemistry with hydrogen and so forth. But also there's a lot of interest in superconductivity now. I'm more interested in the fundamental physics. What is the phase diagram? You know, I'm also interested as a benchmark for simulations. I mean, after all, if we can't do hydrogen, what chance do we have of doing a more complicated material? And it's something they can do experiments on, and we can compare with experiments. It is simpler in that we don't have core electrons. We don't have to deal with pseudopotentials or carry along core electrons. But on the other hand, there's strong quantum effects of the nuclei, either protons or deuterons. And there's a lot of experimental and theoretical interest. This is the group that I work with. I want to mention them. First of all, Marcus Holtzman, who's maybe familiar here at EPFL now, and Carlo Pierleone, another somebody that's come to CECAM a lot. And then these are my group coming out of the University of Illinois, Kevin Lee, Scott Jensen, Ricky New, Shubhang Goswami, and Paul Yang are students at various stages of their career. So I say my COVID team, obviously this is a snapshot from one of our weekly sessions that we've had the last 4 years, talking about these. And here's kind of like the phase diagram of hydrogen. Again, this is on a astrophysical scale. That is, these are many orders of magnitude down to what you might find in a low temperature physics laboratory here, to plasma physics up here, to very dense matter here. In fact, I have the next graph shows you, if you drill a hole in Jupiter, you follow a line like that until you get to the interior. And unfortunately, there are very few ways that you can do experiments in this dense regime. They can do diamond anvil experiments at below 1,000 degrees and below 1,000,000 atmospheres pressure until the diamonds break, or you can do shock experiments where you take something and you compress it using a lot of lasers. And you can get some information in the nanosecond you have of doing the experiment, but not very much information. And so there's a lot of questions in this phase diagram that we want to answer. For example, what is the melting line here? That's the only thing I'm going to talk about because I only have 5 minutes left. But there's also a question of how it goes from molecular hydrogen to atomic hydrogen. Is it a superconductor? Other things. And these are the different quantum Monte Carlo methods that we've applied. But right now we're going to talk about this machine learning aspect in here. Machine learning could be applied to the whole phase diagram. This is where we've actually done the work on. I mean, it looks like a small region, but it is over, an order of magnitude and temperature and pressure. And then if you do direct path integrals, you're up here. If you do variational diffusion Monte Carlo, you're down here at low temperature. And the intermediate region, unfortunately, is the part that's most interesting for experiment. So about 5 years ago, when one of our supercomputers called Blue Waters was going ready for the junk heap, we had like 6 months of time, and we generated this database where we took 20,000 at the configurations in this region of the phase diagram of molecular and atomic hydrogen, where all these points are. We sampled and we got like each point, maybe 100 configurations of snapshots, and we calculated quantum Monte Carlo forces and energies. And so we have something like 6 million data items, and it's actually publicly available. And then we use this database to make various machine learning models, right? And I described how accurate they are. Oh yeah, the thing I forgot to tell you, these machine learning models are a lot faster than DFT. I mean, a lot more accurate, but they're also faster because DFT is order n cubed, but these are order n. So we can easily do 10,000 atoms, and they have actually people provided nice GPU codes to use these models like MACE, so forth. Here's the example of melting curve experimentally. This is the pressure and the temperature, and these are the experiments. And here are various DFT calculations that seem to sort of support the experiments. But when we do the machine learning, we discover something completely different, right? Here is the purported experimental melting curve here. This is what we get for the melting curve, this purple region, and we get a different crystal structure. It's not very different. It's an HCP-derived phase where, successive layers of the HCP lattice distort with respect to each other. And we also get these crystal structures down here. But the fact is we get melting temperature almost twice as high as the experimental melting curve. You might ask, well, how can we justify it? we're trying to justify it. The experiments, first of all, the experiments don't really measure the melting. They just see an anomaly in their experiment in the Raman spectrum. The second is they don't measure the temperature at all. They just infer the temperature based on theory. So there's unfortunately a kind of a circular argument where they rely on the theory to interpret the experiment, and the DFT people rely on the experiment to justify their functional. And so, you know, there could be room for revision of this logic. And so that's what we're trying to do. We're trying to say that, you know, that there really is this much higher stability, and this purported maximum in the melting curve actually doesn't happen. And in fact, what we find is that the melting curve goes up like this, and then it becomes atomic, and it indeed goes down like this. But, you know, that's the work that we're publishing now. And we actually, this shows you that we can get very good agreement with the experiment. Here's the actual clean experiment, X-ray scattering. And this shows the agreement between our machine learning models and the X-ray scattering experiments. And here shows that, that we can actually agree with DFT predictions of melting using the machine learning model. So we are able to use machine learning to replace the DFT and get agreement with the models. But when we train on quantum Monte Carlo data, we get a much higher melting temperature. Anyway, so I think there's kind of like, it's kind of nice that we discovered something new using these machine learning models. We just didn't use it to verify what we already knew. But I think there are a lot of challenges and opportunity, and I hope some of the people here, young people here, could take up some of these challenges. Like, I think quantum Monte Carlo can actually be used as an engine for these machine learning models. But then the question is, what type of quantum Monte Carlo is best? How is best to compute the forces? How to select the configurations to train on? How to speed up the quantum Monte Carlo? You want it to be very robust because you want to just be able to feed into your big network of GPU computers, hundreds of thousands of configurations, and generate quantum Monte Carlo forces. They can have big error bars, but as I said, this is actually good for the machine learning model to have a lot of data to train on. But I am always concerned about putting in the physics into the models, and I still don't know exactly how to do that, how to put in things like long-range interactions and dispersion, and we're investigating this, how to treat the phase transitions in the machine learning model, and so forth. So I guess just right on finish. There's a lot of interest in understanding hydrogen under extreme conditions. That's kind of what we're working on, and with my collaborators. Solid hydrogen is much more stable according to our machine learning models and our quantum Monte Carlo database than predicted by DFT. It's among the most accurate method to calculate the properties of dense hydrogen. And the machine learning, we certainly couldn't have calculated this whole phase diagram and found new solid phases if we were doing quantum Monte Carlo by itself, because we didn't have that much computer time. And so the machine learning definitely helped in doing exploratory physics. So here again are the names of my collaborators. We have somebody new in our team from Grenoble, Metro Vistas, and the other people are here. So I'll stop and take questions.
Thank you, David. And indeed, we have also an online audience. So everyone that wants to ask a question to David can just write it in the question and answer, and Sarah will relay it to us. But also, we are very happy to take a question from the audience. Michele.
Oh, hi.
Hello, thanks a lot. I think I will have questions to ask you offline about this high temperature melting phase, but I have a more general question, which is how much do you see, one of the trends these days is to have machine learning models that are really general purpose, right? General use the model for all kinds of scenarios. And of course, these rely on DFT that for a large part of the periodic table doesn't make any sense. So is there hope that can use Monte Carlo, for F block elements? Because that was my hope, but the more I speak with people who actually practice QMC, this is not so simple.
Yeah, I mean, that's a good question. The question is, I don't know, does the remote audience hear the questions, or I guess I should probably, it's true that in the past, these heavier elements, well, anything beyond hydrogen and helium, basically, take a lot more computer time. But in a way, this is just the history of the field, that they haven't been pushed to do this. And maybe machine learning can help in this, like come up with better ways of doing pseudopotentials and come up with better wave functions and so forth. But again, going back to one of my slides, I think these are real questions that I have, and I can't answer all these questions, is how to improve the quantum Monte Carlo so it can deliver the data quicker, right? Because machine learning is going to require accurate data. And if you train on DFT, you're only going to get DFT quality output. But I think there's a tremendous opportunity to do this. There are methods like auxiliary field quantum Monte Carlo that can treat heavier elements quite well, but they're even more costly in computer time. So, they have to be made faster. There's also the opportunity of doing perturbation. Does that answer your question? Or?
I guess, setting aside the computational cost, let's say that we take, a primitive cell of lanthanide, okay? Yeah. So we just have one or two atoms, so the number of electrons is not much larger than.
Yeah.
Is that something that?
Yeah, we did that actually.
So we can do that.
We did lanthanum hydride, yes. And we found, this is my student Kevin Lee, he found that, there was a phase transition between two different crystal structures using a machine learning model trained on the quantum Monte Carlo. It's possible to do that. In that particular, you happen to pick the one thing that we did. Yeah.
But I guess I'll follow up on this because it's true that you did lanthanum hydride, but lanthanum is actually a very mellow lanthanide. And in some way, the challenge in all these systems lies in the nodal surface. I remember some of the very beautiful work of Michele Casula and Sandro Sorella on the iron dimer. And in some ways, the challenge there was not the quantum Monte Carlo side, getting the sampling, but it was really, getting a good nodal surface. And in particular, the system, you have to explore, different multiplate states and so on. So it's not super easy. So I wonder, if that's really one of the challenges for.
Yeah, it certainly would be a challenge, but maybe the neural network people can solve this problem for us. But for the wave function, like which determinants, in fact, there are papers all the time on this, like which determinants do you need to add and so forth. But the other answer is, I'm not saying that quantum Monte Carlo can do all possible problems. All methods, they have a domain where they work better, and there's other domains where they don't work so well. So, it's a future to figure out where those domains are. I don't know. But in terms of coming up with data like we did on hydrogen, I think there are lots of systems that we can do and generate these kind of forces and energies for to train models on beyond the DFT level.
Please.
So one of the two questions that we have online actually follows
more or less along the lines of what you were saying, because they asked if you think that it's going to be possible to use machine learning or artificial intelligence techniques to overcome or mitigate the sign problem in projector QMC. For example, using them to predict or guide the sign structure of the wave function Hamiltonian in an imaginary time evolution.
Well, yeah, it's certainly possible. The way I would approach it, though, would be to, the idea in the variation Monte Carlo is then you try to use a general antisymmetric function and train and use your neural networks to train that to get the lowest energy. What I would like to do is to try to learn what terms are missing. We already have pretty good wave functions for lots of the periodic table where you start out with Slater-Jastrow wave function, and then you add backflow, then maybe you add something else. Now, but there is sometimes something missing. It would be nice if the neural network would tell us, oh, we have a fourth term that you didn't really think about that you should have put in there with just a few parameters. I think if you're going to use quantum Monte Carlo to generate data, you're going to have a kind of an automatic wave function that you can quickly generate. Somebody feeds in, like we had when we were doing this hydrogen example. We just had a production where we had a snapshot of configurations. We have a standard wave function. We calculate energies and forces. That's it. Put it in our database. No humans are involved in that workflow, right? We want to do that for other elements too, where we have just, and so if we can generalize the wave function beyond Slater-Jastrow backflow and to add more terms, which are kind of automatically put in certain situations, and then you can put it in your workflow and you can get better forces and energies. I mean, I think that's the way I would do it. Now, other people would do it. I mean, if you're at Google or DeepMind or what, I mean, you can choose a lot more computer time and you can do other approaches. But I think if you look at the really successful artificial intelligence applications, they have lots and lots of data. So I think that's the direction you have to go to generate these machine learning potentials.
I'll give it to the audience again, as Sarah mentioned.
Yeah, so there is a question that is specifically about some of the results that you've shown. So why do your models show a distinction between atomic and molecular hydrogen in the phase diagram? Is there an associated dissociation energy along this threshold?
Yeah, do I still have it? Oh, yeah. This is the line between atomic and molecular hydrogen right here. So actually almost the entire phase diagram is molecular, except for this corner right up here, the upper right-hand corner is the atomic. That's one of the big questions. This is called the liquid-liquid transition. And actually we have new results, and I didn't put them in my talk. But the new result is that this line pretty much terminates as a phase transition right here. And it could stick up a little bit into the liquid phase, and there could be a critical point right here, but it's more like water, where this liquid-liquid transition is buried in the solid like it is for ice. You know, there's a long controversy about that. So it's not really a phase transition. What the question was, and so it is likely that you go from the liquid H2 to the liquid H without a first order transition. There's a crossover, and there's a huge, there's definitely something noticeable in the thermodynamics, because obviously the entropy of these two phases is quite different. Sorry, I said phases, I didn't mean phases. These two regimes is quite different on this side and that side. But there is a question, and that's something we actually have a manuscript, and the Dress group has working on this results too, that is this a phase transition or not? And results have differed over the years. People saw a rapid change from the molecular phase to the atomic phase, but they didn't show that it's a first order transition. And so now we think it may not be.
I guess I'll get the last question. So I think the less than new generation are a little bit disappointed that the machine learning works so well. So how it removes the mistakes of quantum mechanics. And so the question is, can we break machine learning? That is there something in the math of quantum mechanics that the math of machine learning cannot capture?
I don't know if let's see. I mean, I don't have any insight there about that question, I guess. You kind of worry about exotic phases, like all these topological insulators or even superconductors or so forth, whether machine learning will be able to capture those things. There's certainly limitations on the machine learning model, which we already see. Machine learning models, the ones that we've used like DeepMD and Mace and so forth, are all short range. And we kind of worry about, like a metal, how is that going to be able to treat a metal? But those are not limitations on the math of machine learning, just on the way it's been implemented. Yeah.
Okay, so we'll think it over at coffee. So I guess we thank again for me, you are not. See, but this is indeed a chance to not only hear the science, but somehow to learn a bit more on what it is to be a researcher, how things started. Actually, how things started, you showed it to us. It was a very nice and refreshing way of looking back at how computational science was done earlier on. So maybe what I'll ask you is, what have been the papers that have really left a mark in your early years, so that you read something and you found that you learned some deep insights that guided you in the future?
Well, I think I mentioned a few of them already in terms of, for example, Feynman's path analysis. A lot of Feynman's, like his book on path analysis, certainly made a big impact. Actually, Feynman's lectures, physics, came out at the time I was a student, and that made a big impact. And that was one of the reasons I went into physics. I don't know if people are familiar with these Feynman's lectures in physics.
I am. I don't know if the new generation is. I am sort of terrified. No, they seem to be familiar.
But I think I described when I came in as a graduate student, I was working on the Green's function Monte Carlo, which was this early version of projector Monte Carlo by Kalos. And I think to almost everyone, it was completely inscrutable but it turned out there was some lecture notes made by Hansen on some lectures that Kalos had given in Paris, where he explained everything. And that was actually a big inspiration to read the still unpublished lecture notes that he had given explaining the method. And then I was able to use these to develop the diffusion Monte Carlo method based on these lecture notes. The other thing that was really important early on was the 1 year I spent working in polymer physics, because there's an analogy between polymers and Bose-condensed systems, which was immediately apparent. So I spent a year learning about the thermodynamics and dynamics of polymers. And that was it. And using that information, I was able to translate it into the path integral description of superfluid systems. So I think that was a big influence. That 1 year I was forced to work in a different area of physics.
Do you still read papers?
Oh, yeah,
Okay.
sometimes.
Sometimes
I have to read papers when I review them, and when I read grants, and I have to correct my student papers and so forth. But I do read some other papers too.
Sometimes I wonder if we are drowning in
No,
too much information.
I certainly only read a few percent of what I should read, but I do read. And also when I was working on writing the last few papers, usually my students have been writing them, but that forced me to read some of these other papers that I'm referring to in my own paper, so yes.
So you mentioned Feynman, I guess, no, did you ever see him lecture, or did you ever see him live? I wonder if, scientific society sort of lacks these days a Feynman or a sort of figure like this that is able to really, bring forward concept in science.
Well, I remember as an undergraduate, I did see a video of Feynman. I don't think that counts, but that was back in the 60s. And then I did actually meet him once in the 1980s at a very small workshop in San Francisco. And that was that was eye-opening. It was actually in the last years of his life, but I did get to talk to him about how we developed the path integral method based on what he had written in the 50s. And yeah, and at that time it was very interested, for example, in quantum computing and in computing in general when I met him in the 80s, because his daughter worked at one of these parallel computer companies. And, he was there as a consultant, and, he talked about some of the new algorithms and ways of doing parallel computing. And it was around that time he made the analogy between whether quantum computers could do things that classical computers couldn't do. Yeah.
Wow. I have to admit that once my car in Boston was broken into, and nothing was touched, but the 6 tapes I had of Feynman lecture were
really?
stolen. So I wonder if it was an MIT student impoverished stealing this. By the way, everyone is welcome also to ask a question here, also on the side. One of the other questions that I like asking is, was there a moment in which you felt for the first time that what you were doing was really relevant?
I think probably there wasn't until this connection between QMC and DFT came along. I think, and that was kind of an interesting story, that I had these calculations I'd done on the electron gas, which to me was an academic calculation. I'd done liquid helium, and I thought, well, uniform electrons, that should be a model more relevant to condensed matter than helium. But that's why I did it. I did it because there were supposed to be experiments in 2 dimensions. And actually, Jean-Pierre Hansen suggested, well, you should do 3 dimensions if you're doing 2 dimensions. And so I did 3 dimensions. And then a few years later, maybe 2 or 3 years later, some people in the DFT community, or the developing DFT community, wanted my unpublished data on the electron gas. And of course, rather naively, I gave them to them, and they developed these exchange correlation functions. And in one sense, that's kind of bad, because I had done all the work and I had developed the same things, the same exchange correlation. I had PAD-A approximates to them and so forth. But it was actually a great thing. It's like how open source works, because they were the publicists for my calculations. And it's like, I say that's like my lottery ticket. that DFT calculator. The fact that everyone started using it in the DFT world was the way I got my job as a professor, right? Because there was a lot of citations and a lot of noise. Which, if I had published my PET-A approximates of the electron gas correlate, nobody would care, right? Nobody would have noticed it. Maybe.
Maybe. I guess DFT has been lucky because after all, LDA is good for reasons that people didn't realize maybe at the time when it was first done. Let's see, Bogdan, do we have anyone online to ask questions? Or yeah, so let's go online. Let's see. Who's there?
Oh, Carlo.
Yeah, hi, David, hi, Nicola. Very nice to see you. Very interesting talk, which I, of course, know quite a bit. I'm actually, for the audience, I knew David, I think he was 92 or 93, in Osua, actually.
Oh,
postdoc, and I think he was in Osua. I was a postdoc with Bernard Bernier in Paris, and it's when we started to work together on hydrogen, high pressure hydrogen, with path integrals. And so that was, for me, was really a change because I was coming from polymer physics, actually. So exactly what David mentioned. And yeah, I wanted to ask you because, of course, Feynman papers, I guess, was very inspiring for what you developed at that time. And you say Feynman was very interested about this application, numerical application that you developed with Roy Pollock. But what about the fixed, I mean, the restricted path? Did you ever talk to Feynman about that?
no.
You didn't have a chance.
It
was too late.
Yeah, when I talked to him, it was before we had that insight about the restricted path. It was just 2 or 3 years before that, yeah. No, I never did.
So no chance to know what Feynman would think about that. Because that's, I think, is something that you, of course, you propose and you use, and we use together also. But then it has remained a little bit underdeveloped, I would say, right?
Yeah. No, I think it is. It is an interesting mathematical result. Whether it would be practically important, I'm not sure. But I mean, the result is not to be too mysterious. You know, Feynman said in that quote that I put up, but I mean, I don't have it here now, but that there's no way to sum up this series of in both systems. You can write the partition in terms of exchanges like pair exchanges, 3-body exchanges, 4-body, and so forth. They just all add up. But in fermions, you know, the even ones have one sign and the odd ones have a different sign. And you know, there's this huge cancellation, and all the interesting physics is obscured by this cancellation. But what we showed was there is some way of getting rid of the cancellation and just having the sum of positive ones. Unfortunately, it requires knowing what the nodal surface of the density matrix is in order to do this. But the question is whether there is some simple ansatz that would give you the rule. And I don't think anybody's answered that question. And
yeah, exactly.
Yeah.
And methodologically, I think is something that would need to be done at some point.
Mm-hmm.
And I don't know what you think about that, because this is a missing piece of information and of I don't know. As you say, maybe it will not be so interesting, but we have seen, I mean, when people do this, for instance, in hydrogen, along the Hugonot, we need to take thermal electrons, right? And nowadays, all these people that are doing high energy density physics, they need sometime thermal electrons, and that would be
Yeah, it could be that
QMC will be the way of doing it.
AI is a way of answering this question, but maybe somebody asked me that question earlier, whether you could analyze when you're proposing paths that say which ones are cross into the wrong nodal regions and should be eliminated. I don't know.
And do you think that, machine learning could learn the density matrix or propose something interesting?
Why not?
Well,
It seems like a big mess to me, but why not? Yeah. No, I mean, we have not even explored the ideas of backflow.
exactly.
Once I started writing the code, it was one of those things I just got lost in the coding and never came out on the other end. But we haven't even, I mean, you could show with some arguments that the backflow is the next correction beyond what we have already, but we haven't even gone that far.
Mm-hmm. Okay.
So this is
Interesting.
already kind of specialized.
So I have a more general personal curiosity, and then there is a question from the audience. You mentioned several times coding and the way you had to code in the very early days and so on and so forth. But then the question is, how did you learn to code? I mean,
How did I learn to code?
Yeah, code.
I don't know. We certainly didn't take any courses, that's for sure. But honestly, in the second year of graduate student, my advisor just gave me this long output listing of somebody else's code and said, well, why don't you modify this and do something a little different in this Fortran code? And so you would just kind of read through it and try to figure out how it worked and how to change it. And then I just started writing my own codes, read the Fortran manuals and learn various tricks that you learn from other people. Other people tell you how to do something and you get some libraries. That was the amazing thing. I mean, there weren't any scientific libraries at the time to do things. For example, I was saying we did everything in real arithmetic because there weren't any scientific libraries that did complex arithmetic. So you just had to learn these things by talking to people. I don't know. When I went to Livermore, it was kind of nice. They had actually mathematicians, applied mathematicians that you could talk to, and they would teach you how to do things that are more sophisticated than what you might think of on your own. Yeah.
We have a question from Gigi, and then I think one from the audience.
I have a connected question. I very much enjoyed when you mentioned casually we worried about efficiency at the time. And so I would also think that maybe some of the, if random person tried to do what you did, for example, on a million times faster computer, it would probably be only 10 times faster.
Oh yeah, I think so.
I think, and so I wanted to ask, so because we also worry about efficiency, but I think I'd say, okay, we worry about the algorithm on a paper, make it efficient, speed up 10 times, 100 times, 1,000 times. But I think we don't have time anymore to worry about hardware optimization, say in our group. That's what you have to really worry. That was also another type of efficiency.
Yeah.
Do you still worry about it also, or just more about the...
Well, I do worry about it, but it's kind of like what do you say? I'm not sure it's something you should advertise, but no, I was going to give an example that, when I did the electron gas calculations, and I don't know if students don't necessarily realize you can write things down like when you're calculating the Coulomb potential. The Coulomb potential is 1/r, right? What are the computer operations you need? You can just write down 1/r, but what are you actually doing when you calculate 1/r? You're calculating, first of all, you have periodic boundary conditions. So I found some way of doing periodic boundary conditions that didn't involve any arithmetic operations, that just to bit masking, and which is a lot faster than arithmetic. And then you get R squared in the end. You don't get 1 over R, you get R squared. But the two operations you need to go to from R squared to 1 over R are the square root of R and the division 1 over R. So those operations, each one is about 20 times slower than an add, for example. So what I did is I made a table of 1 over R as a function of R squared. So I didn't have to do those operations. It was the table lookup. But of course, this works well at low density in the electron gas, but at high density, the particles start getting close together. And because we could only have like 100 table entries because we didn't have more memory, we had problems when electrons would get too close or we get too small. So I had to apply corrections to my results to account for the fact that my table was too coarse. This is the kind of crazy things that we wasted time doing. So that we would gain that factor, we would gain like 10% or 20% speed up in the code because we wouldn't take any square roots in the table.
I think most people forget
Or
about
any
that.
divisions, right?
That actually reminds me the Lennard-Jones potential, that is 1 over R6 is physical, but 1 over R12 is just the simplest thing that you can calculate if you have calculated
Right.
1 over R6.
Right.
Sarah,
That also reminds me, you mentioned Marianne and Sally.
Yeah, I was gonna say more about that.
That would be super nice if you wanted to, but I just wanted to comment on the fact that, when we met her here, she said, I worked with a lot of students and people who worked with Bernie, but the only one who really knew code was David Ceperley.
She knew more than I did. I learned a lot from her, actually, because this is the time the Cray computer, which was the fastest computer, and they had there were like 10 in the world, and like 4 of them were at Livermore or something. And she had been working on these for years, and so she taught me how to vectorize the code. The idea of vectorization was that if you could do vectors of length 64, it would take just a little bit longer than vectors of 1 because it pipelined the whole thing. So it would just go in, like you would say an A plus B, it would just go into the unit for adding, and it would do all 64 practically as fast as doing a single A plus B. And the question, and so since I have around a few hundred particles, I can make vectors out of, like if I was doing Ri minus Rj, I could make vector. You have n squared distances to calculate, and you make vectors out of them, and you do that much faster. And so she taught me how to do that. In fact, she took my code and put a lot of vectorization in it, and she was really great because it was really reliable. The code worked, and she knew about that, and she had set up this system. She had this, I guess we call a mini computer, which is a small computer on her desk that would go around every 10 minutes and visit every supercomputer in the laboratory and see if Bernie Alder's code was running on that computer, because the computers would go down all the time and come up. And then they would come up, and then there would be nobody on the computer for a while, right? So her computer would go around and visit every computer, in a cycle. And she had a way of doing this. And for a while, my production runs were what she did. And I would give her a whole bunch of output. I would say, I want to compute the electron gas correlation energies for these values of RS. And on each cray, she would put a different one there. And when that cray would go down and come up, my run would start. And it would start with a restart, so that if the computer went down for some reason, it would start up in exactly the place that it left off, right? And restart. And then it would just generate more and more statistics. And she was great at doing that, right? And then she would, every so often, she would, like I say, print out the end of the output file and mail it to me in Berkeley. And I would look at it and decide whether it was useful or not, or what I should do in the future. And so, and I would talk to her on the phone every morning, and that was great. But in the end, you know, it's like, because I eventually learned how to program these things, that I had to do it all by myself after she moved into another group. So anyway, that was, she had certainly a valuable co-partner in those electron gas calculations and getting them done. And it was all those years that she had worked with Bernie and doing the same thing with his hard sphere molecular dynamics, which I guess you pretty much wrote the code yourself.
Actually, for the audience here, if you want to see these computers, CPFL as a computer museum, because this used to be a hotspot for Europe for high performance computing. So they had a Cray YMP. They had the first Cray 2 with 64 megabytes of memory, and the first parallel Cray computer in 1994. You mentioned before the Center Irma that Roberto Caro was managing. And so the Cray T3D is there, and you can sit on the benches.
So there is a question from Tisanda Ayuka, who wonders, what are your thoughts on the most important skills for a student to possess going into postgraduate studies nowadays?
Well, kind of depends on the direction that you want to go, I guess. I think in the future, of course, a lot of the work is teams, and I always worked on small teams, like 2 or 3 people, like with Carlo here, or with Roy Pollack or Bernie Alder and so forth. So it was good to develop some good contacts of people you could work with and do something more than you could do on your own, and build up some. But you also want to own some field of your own. That is, you become an expert in something that's important, obviously. And that's a good skill to have, to figure out what's important, what could be important to other people. One of the advice I sometimes give to people that are becoming like an assistant professor, I'm talking about an American university, of course. You want to become useful to some of the other members in your department, do things for them, and so they'll think highly of you. We don't want to go off in your office and close the door.
But so related to this, and before introducing the next mystery guest, suppose that I take out the second magic wand that we use very sparsely, and I remove your PhD, so you have to start again from scratch, and you can't do a PhD on quantum Monte Carlo. So what would you dive into?
Well, I think the whole machine learning thing, of course, I really do think that is the revolution, this part of the century. I'm not so sure about quantum computing, to be honest, but
we share that thought. So let me also, we have another, as you can see, mystery guest here.
I
and
see
let
who
me
that
give
is.
it the word. Paul.
So first, thanks to David and Marvel CECAM for doing this. And I've got, David, sort of 2 related questions prompted by all these historical discussions and your talk. And I was wondering, first, in terms of the evolution of the method since the 70s and 80s, could you describe perhaps one development that really surprised you? And then the second part of this, if you'll indulge, is perhaps one thing that you thought that would happen, but has not happened so far, at least. So one surprising development and one non-development, something that still remains to be done, perhaps.
Well, I have to say, one of the things that surprised me is how successful auxiliary field on Monte Carlo has been, how accurate it is. And this is due to Shi Wei Zhang's efforts, pretty much entirely. That's been surprising. Okay, that's the first. The other thing is I'm surprised the whole thing with the forces has not been resolved. On my list of the top 12 things that I thought needed to be done, that was I thought the easiest one. And that surprised me that people don't do forces. We do forces, but only for hydrogen. And other things, I don't know. Maybe it surprises me that the idea of making black box codes like lamps through QMC is so difficult. That's been kind of surprising. But that's partly because of the evolution of computer hardware that makes it harder, this whole GPU business. If we stuck to CPUs, it probably wouldn't have been an issue. But
yeah, I'll add, I think on your list of top 10 or top 12 things that need to be worked on, I think most of them there's been a lot of progress, but the top one about using forces for general materials, the molecular systems, that's still not quite there, although obviously there's been some progress in the last few years.
Sorry, just this comment on GPUs, modern hardware being so tricky, sort of triggered me, because when I hear your stories about these punch cards and you have to operate by snail mail, it doesn't sound like an easy life, either. So I'm wondering if maybe somehow the tools that we use to interact with GPUs are not up to the standards of professional coders.
This is the kind of maybe my age comment, but I see my students working, and they're working many hours and so forth, but what you accomplish is not a lot more. What they accomplish with tools that are immeasurably better than we had, but what you accomplish scientifically is not so much more, right? And the question is why, and it's just the problems that people are doing are more complicated than we were doing. They're trying to do harder things. If all you're doing was the electron, gas, and helium, you would have accomplished. I mean, I give those problems to students to see if they're able to do anything, right? I often give as when a student comes in and wants to work with me, I say, well, can you reproduce Macmillan's 1964 helium calculation by next week? And because it should be really easy nowadays, right? And it is. But partly it's that the computer languages are still difficult, and the computer hardware is difficult. I don't know. I'm not sure if that gets to the heart of your question or not, but.
Yeah, no, I'm wondering basically how much is it that the problems are harder, how much of it is the fact that, GPUs are certainly more complicated than, but somehow the tools that them should help.
Yeah, they don't actually. Actually, I worked on computers that are really like the GPUs back in the 80s. It was a complete waste of my time to do that. And that's probably like GPUs are. Because I worked, sometimes I'm putting my code on these machines that are only around for a year or two. And after they went away, I just had to throw away all the work that I'd done. And But I don't know, I guess I learned techniques. But
David, if you think back at your career, what is the sweetest professional moment?
well, sometimes there were discoveries that you made that you don't forget, but the one, I don't know, I described the winding number of superfluidity. And I do remember sitting there on the couch, like babysitting and rewriting this paper, and then, this is what it is, the winding number. You know, that was just an instant of time. I think Penrose describes that in his book, where all of a sudden, somehow the neurons connect in your head. And before that, you know, so that was one of the sweet moments like that. And then what Carlos said about restricted paths, and you know, that was again a moment like that where you just remember, this is the way that is. You know, just a great simplification. Yeah.
Great. I think I have one last mystery question. So I'm checking the audience to see if there is one last question from the audience. Otherwise, I go like every second Marvel Classics in the mystery question, and that's the desert island question. That is, if you are going to get sent or just decide to move to a desert island, and you can bring only one book. At the time we used to say one CD. These days I'm not sure what to say. One MP3, one WAV or whatever, one USB for music. What would you bring with you? So one book and one piece of music.
Well, I don't know. Obviously, it would be a very big book. No, I think I would take a math book probably, because I've always wanted to learn more mathematics. So, a book about, I have a big encyclopedia of mathematics, for example. Probably. Yeah,
so hopefully it's a desert island.
One book and one blackboard.
Yeah.
It's a desert island with a blackboard.
Well, you can write on the sand, right? I don't know, music. I like it. I like the 60s music, so I guess I would take some of those, yeah. I just saw this one of Bob Dylan, and I'm not sure the movie was so profound, but it was nice to hear the old music, so.
Okay, so with this, I think we thank David again for all his time. Thank you. Upstairs there is an apero. Correct. Great.
Okay.
So thanks again.
Sure.